Okay, we are live right now, so you can go ahead.
Hey everybody, how are you guys all doing on this wonderful Saturday? So this week we're going to be talking about engineering mechanics, and it'll be presented by FRC Team 3473 Team Sprocket. So right now in the comment section or the live chat, we're going to post a worksheet or kind of like an information sheet for you guys to follow along. If you want to follow along, you can print it out. You can look at it and kind of fill it out. But before I do that, oh, sorry, my computer is acting. Okay, so this week we are gonna do something different. So we want you guys to talk more, but also talk about the important stuff about our topic. So every time one of you guys ask a question on the live chat, we'll have people that are recording how many times you ask a question, and the top 75% of people that asks a question will find a way to reward you and give you a prize for that. So for example, today's topic, how many types of levers are there? So that sort of question, something that relates to our topic for today. Or yeah. Okay. So some updates. Happy Father's Day. So remember to say hey, Happy Father's Day to all your dads. Next week we'll have iOS design and programming, which is hosted by students from UC Berkeley. So they are a real startup. They're really a really cool group of students from UC Berkeley, and they've worked on their app. So they'll teach you how to program an app. So if you guys are really like interested in like Snapchat, Instagram, and that, they're developing a new social media platform basically called Anonymous. Okay, and then in the future we'll have principles of engineering, those type of topics, FTC programming. We'll talk more about EV3 EV3 Lego Simulator. We'll also talk about intro to 3D printing. So those are topics that are coming soon. Okay, and then I want to really quickly go over this. Oopsies. Okay, so I really want to quickly go over this. If you haven't already, please go to our learn.coderina.net website and create an account. I've posted a video. I don't know if you've seen it. Basically, it teaches you how to make an account. I just really want to quickly skim through it right now. I don't want to go through the full 7 minutes, but basically, go to the website here. I don't know if maybe John can post a link into the chat or something like that, and then we can pose. How do I without this bar getting annoying? So basically, fill out this form, fill out your stuff. Oh, this thing is blocking. Okay, go here. Okay, so basically, after you fill out this form, it's gonna have you go to it's gonna show this page, okay? And then after this, you go to your, oh shoot, wrong button, sorry. Okay, after this, it's gonna have you go to your email. It's gonna have you go to your email, sorry, scrolling. It's gonna have you go to your email to verify your account, and then when you click here, after you verify your account, the hard part is to get signed up to the robotics portal. So to get signed up, you have to click on site home, which in this video I haven't done yet, so just waiting on that. Oh, the timeline there, or basically your dashboard is all the courses you're enrolled in, but you haven't enrolled in the robotics course. So go to site home, click on site home. Okay, so site home, and you see Robotics 101 is the first one. So there's all different types of courses you can participate in. Robotics 101 is the first one. And then, what haven't I? Yeah, okay. So click on it. And then they'll ask you for an enrollment key. So your enrollment key is basically, it's this. So if you want to take a picture right now, screenshot your page, you can pause the video and come back to it in the future. So basically, put this enrollment key in, and then Yeah, I'm so slow at talking in this video. Okay, so put this enrollment key, and then you're enrolled in this course, and you'll know what we're doing. It's important that you enroll because we're talking about our CAD lessons. Our CAD lessons, our robotics stuff, our engineering stuff will all be posted on this, and this is how you can communicate with all the students, with all the high school students, and with me throughout the entire week. So here, this I'm just showing you other CAD sessions. Some of you may have already gotten an account made, and Coderina may have already sent you a username and password. So if you might be in that situation, go to your email, search for Coderina in the search bar, and you'll probably see if you. So yeah, around 80 people already have an account made. So yeah, try to join the account. Try to join the Coderina learning portal, the robotics one today, if possible. We're going to be posting our CAD stuff. Okay, so without further ado, let me introduce you to engineering mechanics. But before I do that, let me tell you that engineering mechanics. So today we'll have a heavy focus on simple machines. So simple machines are kind of like the ABCs to engineering. So if you want to learn how to write words, like apple. I want to spell apple. So you know how if you look around you, a car. If you look in a car, you look at your door. You look at. I'm just looking around my room here. If you look at your fan. So these are all simple machines that are put together into a compound machine. And if you want to really understand engineering, this is where we're actually getting started with the complicated stuff. So I really recommend you that you take notes after this workshop is over. Play back and look and listen to the keywords that Team Sprocket will be introducing. Will be saying. So today we'll have Nathan, we'll have Kevin, and we'll have Clarissa from Team Sprocket present to you. And let me hand that over to them.
Hi guys, I just want to thank Kenneth again for the very amazing introduction. So to introduce ourselves again, we are FRT Team 3473 Team Sprocket, and we are a high school robotics team based in Diamond Bar, California. And so today we'll be teaching you guys about engineering mechanics.
Sorry. Okay.
So each year our robots can be broken down into, or each complex machine can be broken down into simpler components. Now you'll see in the screen there, we have 3 robots, and they are the 3 robots that we built in the past couple of seasons. So each year we have a game, and each game has a different objective, such as scoring balls into a goal, climbing a rope, and attaching panels onto a target. And the robots here are designed using smaller components, and they're put together to be one large assembly. Whenever we design our robots, we have to think about the basic mechanics of each robot. And while these robots may seem really complicated and really hard to understand at first, once we get the basic mechanics down, the rest of the process becomes a lot easier. So with that, I'll be talking to you guys about simple machines.
Okay.
So here's just a short video of what one of our robots did last year. This robot was designed to shoot balls into a port. So we'll begin today's presentation by talking about forces. So there are actually 2 kinds of forces. I'm sure you've heard the word forces before. We have the effort force, which is any force that you put into a system. And then the resistance force is the force that you are working against. So for example, in the picture below, we have the effort force shown as the person pushing up, while the resistance force is the weight pulling down. And in this case, the effort force, which is the person pushing up, is working against the weight, which is pulling down on that person. And we'll also begin by talking about simple machines. So like Kenneth mentioned earlier, simple machines are they're the foundation to designing. If you look around you, you look at your door, you look at your fan, those are all simple machines. They exist in everyday objects, and they're really important for our design process. So say you try to open your door at where the handle is. That's pretty easy, right? That's what the door was designed to do. But you'll notice that as you move your hand closer to where the hinges are, opening the door becomes much harder. And that's what simple machines try to make easier. They make everyday tasks like opening doors a lot easier, and they make the process require a lot less force. And to make the definition of simple machines a lot easier to understand, they basically change the distance to change the direction or magnitude for the amount of force required. And there are 6 kinds of simple machines. We have the lever, pulley, inclined plane, screw, the wedge, and last but not least, the wheel and axle. And so work. What is work? Well, whenever you do something, you have to work to do it, right? Well, in design, work is simply the amount of force that you apply over a set parallel distance. And so in a simple machine, the work will never change. However, the amount of force or the distance needed to travel will change within work. So simple machines make it so that you can apply less force to make something happen while increasing the distance. And this makes it easier on the person using the simple machine to complete the task that they're trying to do. And with that, we can now understand what mechanical advantage is. So mechanical advantage is basically a value or a number that tells you whether or not you're using more distance or more force when completing a task. A task has a set amount of work. So again, that amount of work will never change. But having a high mechanical advantage means that you're using less force, but increasing the distance that you need to travel to complete the same task. And vice versa, having a smaller mechanical advantage means that you are increasing the force needed to do something while decreasing the distance that you're traveling. So if you look in the top right corner, you'll see a picture of an inclined plane, a yellow box, and an orange box. So in the orange box, in order to reach the top of the inclined plane, the person lifting up the orange box will have to apply more effort force in order to reach the same destination as the yellow box. Now, that means that the work done on the orange box will have a lower mechanical advantage because you are traveling a shorter distance but increasing the force done on the same task. With the yellow box, you have a longer distance to travel but a shorter or a smaller amount of force required to get to the same destination. So essentially, mechanical advantage is just comparing the amount of distance or force used for a set amount of work.
Hey Nathan,
Yeah.
the chat wants you to slow down if you can.
Oh, okay.
A bit. Yes.
All right, yeah.
Thank you. No, you can continue.
Oh, yeah. Next slide.
Okay.
So there are 2 kinds of mechanical advantages. We have IMA, or ideal mechanical advantage, and AMA, which is actual mechanical advantage. So IMA, or ideal mechanical advantage, calculates mechanical advantage using the distances that the effort force and resistance force are located from the fulcrum, while AMA, or actual mechanical advantage, describes mechanical advantage based on the physical properties of the effort and resistance forces. So the reason that they're calculated differently is that IMA uses distances, and distances stay constant. They're less likely to change than the physical properties of force. However, in AMA, it is a more accurate calculation of mechanical advantage because we consider things like heat and friction, which I'll discuss later on. So basically in any system, factors such as friction will result in heat and energy loss. So if you think about a car or a bike, so after a long ride, you'll notice that the car engine becomes really hot. And that's because the energy that was used to make that engine run, some of that energy was converted to heat. And so since heat is also energy, you're going to need more energy in the system to compensate for whatever energy was lost through heat. And finally, like when I mentioned IMA and AMA earlier, we can actually use these two values to calculate the efficiency. So essentially, efficiency is just comparing how much work you put into something and how much work you get out of it. So it's like describing if you put how much, like the amount of effort you put into making something work and how much of the effort that you put in actually gets contributed to your final result. So let's think about it like boiling a pot of water. So if you pour some volume of water in a pot and you have that initial amount of water, right? After you boil the pot, some of the water will be evaporated and get lost in the air. So while your final result is that you still have a boiling pot of water, you won't have all the water in there that you initially poured in. So in the same way, it kind of works with energy. That the same process can be put with energy, where not all the energy that you put in a system is contributed to the end result. So for any system, it's basically impossible to achieve maximum efficiency or 100% efficiency.
Okay, hi guys, my name is Clarissa, and today I'll be going over the 6 types of simple machines with you, and Kevin will come in every once in a while to show you examples of simple machines on our robot. So to kind of recap, work is anything that you're trying to do. So like if you're trying to move a rock from one place to another place, that's an act of work. And mechanical advantage tells you when you're doing something, when you're doing a certain amount of work, will you be using more distance in the process or will you be using more force in the process? So it kind of tells you that comparison. But yeah, with that, let's get into it. So our first simple machine is levers. Levers come in 3 parts. You have your effort force, resistance force, and your fulcrum. A resistance force in parentheses over there is also called your load because like when you're carrying something, it's a load, right? So those 2 words are interchangeable. Our fulcrum in the center bottom is our pivot point of the lever. It's the point where the force kind of circles around in a lever. So if you remember, your effort force is basically the force that you will fight with, whereas your resistance force is the force you're fighting against. So in the example of the little cute GIF in the middle, the blue and orange boxes are both effort forces and resistance forces. It's just depending at what time they're slamming down or the time they're being lifted up. In the case when they're slamming down, they're the ones putting the force on the system, so they would be the effort force. Whereas when they're being lifted up, they're providing resistance. They're the load, so that's the resistance force. Yeah. So next, we have our 3 types of levers. First class lever, second class lever, and third class lever. All these levers are based on the relative positions of the forces, and that sounds a bit complicated. So the way we like to think of it is just look at whatever part is in the middle. So in the first class, you can see that the fulcrum is in the middle. And then in the second class, you can see the load is in the middle, third class, you can see the effort is in the middle. And I'm not sure if you guys can see the words, but red is effort, fulcrum is the triangle, and then the green is the load. So what that means is not all levers are going to look the same, as you can see by the examples on the bottom, but you can kind of figure out what it is. So for the first class lever, again, the fulcrum is in the middle. So that's like that, if you can imagine. And going back, mechanical advantage can be calculated as distance to your effort force compared to your distance to your resistance force. So in this diagram, you have the fulcrum in the middle, and then you have your effort force on one side, and then your load on the other side. So mechanical advantage, since it can be calculated as distance to the points, it can really vary for a first class lever, because you can have your effort force really far away, or you can have your load force really far away. And as long as you put one over the other, then you calculate the mechanical advantage, right? So yeah, it's really variable to calculate mechanical advantage for first class levers. It can change regardless of where the forces are placed. If you can look at the scissors at the bottom of the screen, that's an example of a first class lever, because the fulcrum, the pivot point, is in the middle, where you have the little pin of the scissors. And if you, the best way to put it is kind of like a seesaw. I saw it in the comments. You just kind of open it up and close it. So yeah. Moving on to our second class lever. Second class levers has the load closer to the fulcrum than the effort force. Again, mechanical advantage is distance to your effort force over your distance to the resistance force. So in the picture, the distance to the effort force is the red arrow, and then the distance to the resistance force is the green arrow. So it's going to be a big number over a small number. So that's why mechanical advantage is always greater than 1 in second class levers. So remember, what this means is that the force that you put into your system will always be less than the force you can carry. Basically, with second class levers, you can carry heavier stuff than actually putting in that same amount of force, if that makes sense. Like, basically, second class levers are cool because it's a way for you to seem really strong when you might not be. I guess that's the way you can put it. You can put in more. You can put in less force, but carry the same heavy amount of heavy objects. So a suitcase over here, you can see that the fulcrum is in the wheels, and then the load is in the center, while the effort force is the person carrying it from the top. So that's how it all interconnects. Again, differently, third class levers has the effort force closer to the fulcrum, so the red arrow, and the load farther away from the fulcrum, so the green arrow. As you can assume, we're going back to the mechanical advantage definition. Mechanical advantage definition is distance to the effort force over distance to the resistance force. So the distance to the effort force here is the red arrow, so it's going to be a small number usually. And then that distance to the load or the resistance force is a big number. So you're going to put it a small number over a big number. And that's why mechanical advantage for a third class lever is always less than 1. So what that means is that for a certain amount of force, say you have like 5 pounds of something, then you'll probably need more than 5 pounds to carry that 5 pounds because you're closer to the fulcrum. You're trading more force for less distance to the fulcrum. Yeah, it's kind of like just a trade-off. So now we're gonna be playing a quick game of guess the lever. So in the comments, I want you guys to just spam, I guess, what you think the lever is. And before we start, it's kind of helpful for you guys to draw a force diagram. So you might be asking, what's a force diagram? So a force diagram is just a basic drawing that shows where the forces are acting on a system. So if you guys have like a notepad or something you're taking notes on, you can just kind of draw a line to act as, you won't be able to see that. You can draw a line on your paper to act as the wheelbarrow over here, and I'll help you out for the first one. So in the first one, on the far left, you can draw a small triangle underneath the left of your line, and that will be your fulcrum because the wheel is the fulcrum. And in the center, you draw an arrow from the top because that's your load, and then on the right for the wheelbarrow, you draw an upwards arrow because that's your effort. And then you can label them effort, resistance, and fulcrum, and hopefully, based on your notes, you can infer that this is a second class lever. So yeah, I saw a lot of you got it right, so that's great. Okay. Well, you guys can guess this one, or you guys might have already seen this. But guess what this is? The fulcrum is at the very top, the resistance force is at the very bottom, and then the center is where your hands are, so that's the effort force. Yes, this is a third class lever. Okay. A crowbar. Can any of you guys guess what this is? So for this one, actually you have your fulcrum at the very bottom, so where the end of the crowbar is, and then you have your resistance force at the next corner, if you see the small corner leading up to it, and then you have your effort force at the very back where you're pushing down. There's a lot of varied answers for this one. Some say third, some say first, and some say second. Interesting. Yes, but this is a second class lever. Yeah. Make sure to compare it to your force diagrams, and you guys can always go back later. Okay, this is one that we kind of mentioned earlier, but this, hint, hint, it's kind of like scissors, right? If you think about it. So you have, so you have your effort force on the right side, and then your resistance force on the left side, fulcrum in the middle, so this would be a first class lever. Hope you guys got it. Okay, so next, have tongs. I almost forgot what these were. Yes, these are tongs. And you have your fulcrum, which is the pin in the back, and your resistance force is at the very bottom, and then your effort force is where your hands are grabbing them in the middle. So in the center would be your effort force. If you remember, there's only one type of lever with the effort force in the center, and that is third class lever. Hope you guys got it too. Okay, well, this is our last one, and it's kind of tricky, but the fulcrum for this one is also at the very bottom of the fishing rod, and then where your hands are, that would be where your effort force is, and then at the top would be your resistance force, where you're pulling back your fish, right? So your center is the effort force. Center is effort force. There's only one of them. That is a third class lever. So to all of you guys who got it right, congrats. To all you guys who are trying, there's a lot more examples out there, and it's a work in progress. Don't worry, it took me quite a while to absorb everything, so don't worry about it. Okay, before we move on, there are two more technical definitions to add to your list. First of all is your torque definition. So torque is a force that creates a rotation that creates rotation or torsion, which is a twisting force. So this kind of relates back to our lever because our lever, remember, has a fulcrum, so stuff can twist around it. So that's how torque relates back to it. Moment is actually kind of it's more broad than this. There are different kinds of definitions depending on where you apply this, but in context for what we're talking about today, moment is something that measures torque. Moment is calculated by distance times perpendicular force. And if you remember work is distance times parallel force. So it sounds similar, but it's not. Yeah, so moment explains torque, so a rotation force, right? Whereas work explains you giving the process of doing something, right? Just work is work. So work explains that process. So don't get them mixed up. If you can see by the diagram, moment equals distance times perpendicular force. So if you see the lever, it's a perpendicular force. If you guys don't know what perpendicular force is, it's 90 degrees. Yes. Hopefully that makes sense. Okay. Oh, and to the person in the comments wondering if that picture was a first class lever, yes, it was. So our second simple machine, I mean, that was a lot, right? But we're only on our second simple machine, is the wheel and axle. I'm sure a lot of you guys are more familiar with this because we probably see wheel and axles in our everyday lives, right? So in a wheel and axle system, the axle is always the smaller rotating part. And then the wheel would be the bigger rotating part. A wheel and axle system is based on the principles of a lever, if you can see by the picture on the left. So you see the pink arrow is the force from an axle, and then you see the blue arrow is the force from the wheel, right? So either you can drive the wheel and then make the effort force that blue arrow, and then the resistance force the pink arrow. Or you can flip it around and then you drive the axle. So in that case, the effort force would be the pink arrow, and then the resistance force would be the blue arrow. So there's a lot of ways to play this out. So if you can see on the bottom, there's a lot of different examples of wheel and axle systems in everyday life, from a steering wheel to a doorknob, even to a pizza cutter. There's a lot of ways that it's used. But yeah, let's move on to calculating mechanical advantage for wheel and axle systems. Okay, so again, for calculating mechanical advantage, you can use distance or forces, because if you remember what Nathan talked about earlier, ideal mechanical advantage uses distances, whereas actual mechanical advantages use forces. So when basing, so our first one is when you're basing your wheel and axle off of a third class lever, if you can use the picture on the left hand side, the effort force should be closer to the fulcrum than the resistance force. This kind of relates back to your force diagrams, right? So your effort force would be that pink arrow, and then your resistance force would be the blue arrow. So take our picture, the wheel, right? So in a wheel, in the wheel of a car or a truck or anything, you have the axle in the middle, driving the wheel. So the axle would be the effort force, and the wheel would be the resistance force, or more like the wheel touching the ground. That would be your resistance force. You're fighting against that. Okay, so remember, third class lever is an axle driving the wheel scenario. That means the effort force has to be a lot more, because if you ever had, like, imagine trying to move a car, right? like if your car broke down or something, it would be a lot easier to grab it by the wheels and move it forward, right? Than try to grab it by something small and then try to like push it forward, right? Your force that you need to put on an axle is so much higher than the force that you would need to put on a wheel. However, your trade-off for that, your effort, your distance for your effort force doesn't need to be as much, because if you imagine grabbing a wax axle, you only have to turn a little bit, right? Whereas with a wheel, you have to turn a long way before you complete one rotation. So in this case, where your effort force is increased a lot and your distance is decreased a lot, that's where your mechanical advantage is less than 1. But in this scenario, it's good because that means your wheel is traveling a lot farther, and that's the basis of a car, right? So I hope you guys got that. Oh, can I go back? Thank you very much. Going to the next section, basing the wheel and axle off of a second class lever, the effort force is farther away to the fulcrum than your resistance force. So your effort force would be the blue arrow, and then the resistance force would be the pink arrow. In this case, it's a wheel driving axle scenario. So the best example for this is a steering wheel. A steering wheel, you grab it by the wheel and turn it, right? And you have to travel a long way to complete one rotation, but it's easy to turn. So in this case, the effort force is low, and then the distance you have to travel is high. And the mechanical advantage then is greater than 1, because mechanical advantage is distance of your effort force over distance of resistance force. And next we'll have Kevin kind of explain to you how we used wheel and axles on our 2019 robot.
This is our 2019 robot, JMH 3.0. As you guys can see, we use a wheel and axle system with the green wheels at the front of our robot. These wheels are driven by the axle, so they have a high mechanical advantage as we're spinning them with electrical motors. This allows us to spin the wheels really fast to help us take in and spit out the orange ball, as you guys can see on the right of the robot. And here's an early video of an early iteration of a robot taking in a ball and shooting it out.
Kind of talking over the video since it doesn't have sound. Oh, that was per video. Never mind. So the goal of this game, well, for the part where we use the balls, is just to put balls into like those little goals. If you can see, there were low goals and high goals, but for our team, we decided to be mostly adept with using the low goals. So if you can see, our robot is just trying to shoot balls into that goal. So moving on, we're going on to our third simple machine, which is a pulley. And a pulley is just a wheel with an inside groove to hold a rope. And the way pulleys are different is not only can they change mechanical advantage, which is the same as all the other simple machines we were talking about, but it can also change the direction of a force. So just imagine a pulley and a rope going through it. If you pull down on one side, the pulley on the other side will go up, right? So pulleys, for this reason, are often very useful, but they're often very inefficient as well. And what do you think the reason is? Oh, it's right there already. Well, the two reasons for inefficiencies in pulleys are friction and rope angle. So when you have friction, right? Like imagine a rope sliding against your hand. If you pull it too fast, you feel a lot of heat, right? So friction causes heat, and heat is energy. So whenever you're putting energy into something, it has to be coming from some place, right? So when energy is going to that heat because of friction, you'll need extra energy to compensate for that lost energy. So that's why pulleys can be inefficient sometimes. Another thing to add is rope angle. Rope angle, if you remember, work equals force times parallel distance, right? But in a pulley, sometimes, like if you see in the picture, you have your ropes kind of slanted. So it's not parallel, it's slanted. So in that case, your forces are not directly going in the direction that it's supposed to be going. So your calculations are going to be a bit different. So that's how rope angle affects it. You'll have to put more force in. Okay. Moving on to our two basic types of pulleys. First, we have our fixed pulleys, and then we'll have our movable pulleys. As you can see by the diagrams, fixed pulleys is just one pulley and a rope going through it. Like if you're grabbing water from a well, you pull down on one side and then the other side goes up. It's the force just changed direction, and its ideal mechanical advantage is 1. So what that means is the force you should be putting in and the force you're getting out should be about the same. The distance you're traveling on one hand and then the distance something else is traveling back on the other hand should be the same. But remember, for pulleys, often it's kind of inefficient. So that means that the force you're actually putting in and the force that you should have been putting in, they can be different. Oftentimes you'll be pulling harder than you would have to in a theoretical world, in an imaginary world. And also we have our movable pulleys on the right. So a movable pulley, if you can see by the point A, it's attached to something. So whether it be a bar or like the ceiling, and it has 2 pulleys instead of 1. So in this case, when you pull down, something else I think in here is like a weight or a bell. It's also being pulled up. So pulling down. Pulling down and going up. The IMA for this is 2. So what that means is that the effort force is halved. The effort force is halved, and then the effort force is halved, but you have to travel farther. So you increase your distance while trading it for force. Going on to our next slide.
So this is our 2020 robot, and you guys can see many different kinds of pulleys on this robot. The main ones being the orange belt. You can see going to the back and to the top of our robot. And so we use pulleys on this robot to help bring in the yellow balls to the back of our robot and then to the top of the robot so we can help shoot them out. Sadly, we don't have a video of the robot doing this, so you guys are just going to have to imagine it.
The final 3 simple machines are a little bit easier. Our first simple machine is an inclined plane, which is just a flat surface raised at an angle. And if you guys had trouble understanding ideal mechanical advantage or actual mechanical advantage from earlier, inclined planes are the best way to put it. So if you see on the left-hand side, on the bottom, the distances, you have 15 feet and 4 feet. Those distances will never change based on friction or anything like that when you're traveling to put a cart up. But the forces can change. So it says here you have 50 pounds and 20 pounds. Those forces are subject to change based on friction and heat loss and all that.
This is our 2017 robot, JMH 1.0. This robot uses an inclined plane, which you can see with the white plastic on the top of the robot, to help us transport the gears, which are dropped on top of our robot, to the front of our robot, so we can travel quickly across the field without having to spend a lot of time trying to grab the gear. And here's a short video of that happening.
Okay, so our fifth simple machine is a wedge. And a wedge is made by a moving inclined plane, as you can see by the angle. And what it can do is split something, like when you're hammering in a nail, or it can tighten something, and it can also raise heavy objects. If you put a wedge underneath something and you kind of hammer it in, it can slowly increase its height over time. And on the right, again, you can see how ideal mechanical advantage and actual mechanical advantage can be calculated. First was ideal mechanical advantage with distances, whereas actual mechanical advantage uses forces. And our sixth and last simple machine is a screw. So a screw is an application of the inclined plane and the wheel and axle. So an inclined plane on a screw kind of is the wrapping part around the cylinder. You can see it goes at an angle, whereas the wheel and axle is the motion that you do when you screw in something. You just kind of turn it around in the rotational motion, right? A circular motion. So this converts rotary motion into linear motion. And rotary motion is again just like a circular motion, whereas linear motion is a direct motion. Yeah, very large mechanical advantage for a screw. So that means you don't need a lot of force when you're driving it in, but the amount of distance, like imagine turning it a long time, that it needs a lot. So it's helpful when you're putting stuff together. Yeah. And finally, we have compound machines. So a compound machine is a combination of any simple machine, really. The mechanical advantage of multiple simple machines put together is multiplied. So compound machines are very helpful. Like for example, on our bot, it's a little more complex, but that's because we use compound machines. We put stuff together, and the reason mechanical advantage multiplying together is great is because you can increase your force drastically or increase your distance drastically when putting one and one together. But yeah, next we'll have Kevin.
And with that, we'll be moving on to different types of ways to transfer rotational force or torque. And we'll be starting with gears. Gears are circles with the teeth on the end of them that transfer torque, which is rotational force, by having the teeth on the gears meshed together. A gear ratio is how fast one gear spins in relation to another. So for example, if you see the green and red gear, if it were a gear ratio of 2:1, the first gear would complete 2 whole rotations before the second gear completes 1. Next slide. And in order to calculate a gear ratio, there are important variables you need to know. The number of teeth each gear has, the diameter of each gear, the speed or angular velocity of each gear, and the torque. Now, all these variables are interchangeable because you can calculate it using the equation at the bottom, where you divide the output gear and the input gear, and that would give you the gear ratio of any of these variables. With the only exception to this rule being speed, where you'd have to divide the input by the output instead of the output by the input. When individual gears are put together, it creates a gear train. A gear train is a system of gears where the first gear transfers torque to the gear at the end of the gear train. The first gear in the system is known as a driver gear, as it's the gear that causes motion, while the last gear is the driven gear, as it's the gear being driven by the first one. Every other gear in between the driver and driven gear are known as idler gears, and these gears are either used to help increase the distance between the first and last gear, as sometimes your input is not at the same location as your output, or you want to change the direction of your spinning gear. As you can see in the image, when 2 gears are put together, they'll spin in the same direction. They'll spin in opposite directions. However, if you want your input and output gear to spin in the same direction, you need either gear in between them. Now, here's an example of a gear train with either gears. that our team has made. And so we use this gearbox to help our robot climb. And as you can see, the center gear is the driver gear, while the gears on the end are the driven gear. A special type of gear train is known as a compound gear train. Similar to a compound simple machine, it multiplies the gear ratios so that the individual gear trains together either increase the speed or the torque of the system. In order to create a compound gear train, two gears must share the same axle, so it makes the gear. When gears share the same axle, they share the same speed. For example, gear A is driving gear B, which is to make the speed lower as it has less teeth than gear B. And since gear B and C share the same axle, it makes it so that C also spins slowly despite having a small amount of teeth. And then a separate gear train from A and B would be gears C and D. And this is a compound gear train because whatever happens to gear A, whatever input is put into gear A, the output of gear D will be affected by the individual gear ratios of each system. Here's another example of a compound gear train, where, as you can see, the middle gear is being driven by two side gears. And then because of the middle gear is being driven, it drives the smaller gear on the same axle to the larger gear on the axle below it. So another method of transferring torque would be a chain and sprocket system. A chain and sprocket system is similar to a gear train because of how fast sprockets can spin and how much energy is transferred. The speed of a sprocket chain system can also be calculated with the gear ratio. However, it's different from sprockets as instead of the sprockets meshing together, rotational force is transferred using the chain instead of the individual sprockets touching each other. And also, the two sprockets will spin in the same direction despite not touching each other, despite there only being two in the system. Next slide. A belt and pulley system is very similar to a sprocket chain system, as you can interchange the parts and it'd be the same thing. A pulley is interchangeable with the sprocket, while a belt is interchangeable with the chain. Now, these are similar. The only differences from a belt and pulley is that your pulley does not have the teeth variable, so that you would have to use the other variables to calculate your gear ratio. Now, you guys may be thinking, if chain sprocket and pulley belt are so similar to each other, what's the difference between them? A chain and sprocket are very strong, so you can transfer high amounts of torque or rotational force, and there's no chance of the chain slipping off of the sprocket. However, chain and sprocket, you need a separate type of lubrication like grease or oil. They can be loud, and they have the tendency to break if your torque is too high. While a pulley and belt, on the other hand, is very quiet and there's no need of lubrication. And however, a belt has a chance of slipping off the pulley, and belt can only come at specific lengths. So it's hard to get belt at specific lengths or for whatever you need unless you order it for that or design around it. After talking about different methods of how torque can be transferred, we'll talk about what can create rotational force. A very common method would be an electric motor. An electric motor works based on the two important parts of a stator, which a stator is a magnet that lies on the edge of the motor, while a rotator is a coiled wire that is connected inside the stator, which is connected to a communicator. The communicator will take in electrical signals from the terminals and sends it to the rotor. The rotor will then spin based on the communicator, reversing the polarity of the electrical signal. Polarity is how attracted something is to a magnet, like its north and south ends. And so since the polarity changes every half rotations due to the communicator, the polarity helps keep the rotor spinning. We're gonna move on, and so a video is gonna help show this, and we'll help explain it a bit further. And so as you can see, the rotor is a large amount of coiled wire which spins in between, and the outer shell is the stator. You can see the polarity here working as the communicator will change the polarity, which changes the north and south ends of the wire. It changes the north and south ends, and since it's the magnet that surrounds the motor, the changes will constantly try to move away from the similar types of tractions, and so that's what keeps the motors constantly spinning, as long as there's an electrical system being sent through. Next, we'll be talking about
we'll talk about manufacturing tools and machines next time. We're out of time, unfortunately, but please, we'll actually talk about this. So there's actually this is important. So it deals with manufacturing, so like fasteners, drills, bandsaws, chop saws. We'll talk about that in the Principles of Engineering lecture workshop. So right now in Zoom, we're having a Zoom session today at 5:10 Nigeria time. So we have around maybe 10 more minutes until that one starts. So thank you. Not on YouTube because we want to Zoom. So if you've noticed with Onshape, everyone, we're communicating with each other. We want to help you if you have a question, and we don't want to just be reading the chats. We want you to be talking with us, and we want you to be engaging with us. So join the Zoom session for Onshape. We'll teach you how to use Onshape, and this is the session. If you guys have any questions, do comment here. And thank you so much for Team Sprocket for today for helping us with this session. Thank you, Team Sprocket.
Kenneth. Yeah, thank you, team, for a wonderful presentation. And I think all the learners will still have to come back here some other time to get the right. The presentation link is going to be on the Coderina Learning Portal. So we're going to. It's already there because Kenneth has actually posted things there. So you could actually check it out and try out with it. So now we have 10 minutes thereabout to get to the chat session. So please, you can actually go, but for now you can still ask your questions and all that, because I think from what I was looking at the chat, several people still need some. So Kenneth, are there going to be further samples that you could actually share perhaps on the learning portal for learners to actually go into?
I'll have Team Sprocket prepare more examples. I think the worksheet, I've not actually seen it myself, but I think the worksheet should be really helpful.
Yeah, I shared the worksheet the other time, so I'm still going to share it. But yeah, but the bottom line is that now, if there are more examples,
and more examples, we'll put more examples and more examples of simple machines. We'll put more examples of levers with levers. We'll put more all of that in into the portal. So
all right, great.
And get more people to make a portal. And all that.
Yeah, exactly. So Kenneth did a wonderful job by introducing you to the portal. So if you get to the beginning of this presentation, you'll be able to understand how to get into the portal. I shared the links already. You go to learn.coderina.net, and then you could actually get on through. It's something that you should be able to get. But if you have any issues, you can actually get back to us at hello at coderina.org for you to get into the portal. So we want them to transition to the Zoom class, and at the same time, maybe take a glass cup of water or something before they get to class. So thank you, team. It's really a nice presentation. I enjoyed even listening through the process, and it's really making engineering to come very close to every kind of learner that you might have here. So thank you very much. So we'll see you in the other class.
Yes, so thank you, Team Sprocket. They have done an amazing job explaining simple machines today, and they'll definitely be back to tell you more about principles of engineering.
Thank you guys so much for this opportunity. For some of us, it was our first time doing this, so
wow,
yeah, it was kind of exciting. But yeah, thank you guys so much.
That's interesting. So it's a whole lot, and we really had a nice time. Your slides looks very convincing and very nice, and
yes, they put in a lot of work into
exactly. And Clarissa, yeah, thank you. Kevin, thank you. We really appreciate you. Nathan, so are they the ones going to present next week too?
Next week it'll be a special guest speaker from UC Berkeley. So they're actually making app design. So they'll be doing iOS app design. So they'll teach you about how to design an app, how to program it, and basic introductions. Yeah. So it's next week will be really cool.
That's very nice. That's very nice. Can I know what on what platform are they teaching on the app design?
I have no idea actually.
Okay, good.
Yes,
so we need that too for all our learners to kind of like.
They'll be using StreamYard if that's and YouTube. But I'm not sure of if they're doing a Google Slides. They said they have something awesome to show us. Yeah, and they're really, they're a startup company, so they're just
Woo! I think we're going to make more announcement about that. All our learners are going to really come around and see.
Yeah, so they're really they've been preparing for like 3 weeks on this. So yeah, you should.
Really?
Yeah,
wow,
they've been really
that's
excited.
Cool. That's cool. That's cool. Yeah. So we'll look forward for that. So let me allow you guys to.
Yeah.
You said?
I think 2 weeks from now, I think we'll do another one on engineering. Give these guys a break because of everyone has been. It takes so much time to make a PowerPoint slide.
Exactly. I agree. So thank you, team.
Thank you so much.
Really appreciate you.
And I'll see you guys in the CAD session. So remember to go to that. A lot engineers, you guys will really need to know how to do CAD. Trust me. I'm doing it on a daily basis.
Yeah. So I'm going to drop the link one more time so that you're going to be. Yeah, I'm dropping in the chat so that. Yeah. So we'll get to see you in the CAD class. Yeah. So I'll be ending the broadcast in 2 minutes. Thank you, team. So I'm going to be putting you off the screen right now.